Okay, right. We are still on the topic of air compressors, reciprocating air compressors. What we are now going to talk about is work done by a reciprocating compressor. Okay, the function of a compressor is to take a sufficient amount of air and to increase its pressure. Compressors may be classified into different categories. Some of them are reciprocating compressors, and then you also get what is referred to as rotary compressors. Okay, etc. Each has their own advantages and disadvantages. As we know, the reciprocating compressor may be used for high pressure applications. Now, let us consider the following for a single stage, single acting reciprocating compressor without clearance volume. Okay, let P1, V1, T1 be the pressure, volume, and temperature of the fluid before compression. Okay, now P2, V2, T2 be the pressure, volume, and temperature of the fluid after compression, and R be the compression ratio, simply meaning your compression ratio is going to be P final divided by P initial, or P2 divided by P1. Okay, right. Now, let us discuss the PV diagram of a single acting, single stage reciprocating compressor without clearance volume. We will note that in figure 5.5. We are now going to get there. In this diagram, the path 1 to 2 represents the polytropic compression. From the above diagram, it is clear that the air is drawn in by the cylinder during the suction stroke. That's 1 to 2. Okay, the air is compressed during the compression stroke, which is 2 to 3, and at constant temperature, simply meaning temperature is constant. T initial is equal to T final. Okay, now the pressure rises from P1 to P2, from 2 to 3. Okay, right. The air will be delivered when sufficient pressure has been reached so that the valves can be opened. The delivery, okay, the delivery of the air takes place from 2 to 3. In brief, 4 to 1, suction stroke. Okay, air is drawn into the cylinder. Now the volume of air is V1 at P1 and T1. Okay, right. So if we look at 1 and 2, it talks about the compression stroke. Air gets compressed into the cylinder according to the law PV to the power of N equals the constant from pressure P1 to P2. The volume then decreases from V1 to V2, and the temperature increases from T1 to T2, and then from 2 to 3. Air is delivered under pressure at V2, P2, and T2, and then 3 to 4. What's happening there is that your delivery closes and the suction valves open for admitting fresh air inside the cylinder. Okay, right now. Okay, right. So now we are going to discuss the theoretical PV diagram neglecting clearance. Simply meaning clearance is it's not accounted for. It's unaccounted for. Okay, right. In this diagram now, the path 1 to 2. Okay, 1 to 2, here's 1, okay, and then there's 2. That there's a pathway there. Okay, it represents a polytropic compression. Polytropic compression, simply meaning polytropic, it is PV to the power of N, and then that will equate into a constant. That's what we refer to as polytropic. Okay, it's polytropic compression. It's a path from 1 to 2, polytropic compression. Okay, it is clear that the air is drawn in by the cylinder during the suction stroke 1 to 2. Okay, simply meaning from 1 to 2, there is what we refer to as a suction stroke. Okay, the air is compressed during the compression stroke from 2 to 3. So simply meaning this here, it is a polytropic compression from 1 to 2. It's polytropic compression. Okay, and then another thing that is clear is that the air, it is drawn in by the cylinder during the suction stroke, which is from 1 to 2, polytropic compression. Okay, sucked in, and then the air is compressed during the compression stroke. Now there's a compression stroke, and the compression stroke is referred to as 2 to 3. at constant temperature, simply meaning from 2 to 3 temperature remains what? Constant. Okay, simply meaning our T1 is equal to our T2. Now the pressure rises from P1 to P2, simply meaning pressure is now rising from P1 to P2. Okay, from 2 to 3. Okay, right, simply meaning between 2 to 3 pressure is rising from P1 to P2. Okay, right, now the pressure is rising from P1 to P2 during the stroke of 2 to 3. Okay, right, now the air, it will be delivered when sufficient pressure has been reached so that the valves can be opened. When the delivery of air takes place from 2 to 3, simply meaning 2 to 3, there's what? Air take. Okay, the delivery of air take, it's taking place between 2 to 3. Okay, right, now in brief, if we go and we say 4 to 1, from 4 to 1, okay, from 4 to 1, what's happening from 4 to 1? Air is drawn into the cylinder, meaning volume of air V1. Okay, then it's at P1 and T1, simply meaning this is this point here, number 1, we refer to it as P1 as well as T1, but note T1 is equal to T2. Okay, right, now from 1 to 2 compression stroke, okay, the air gets compressed into the cylinder, and then according to the law, which is PV to the power of N, which equates into a constant from pressure P1 to P2, P1 to P2. Okay, right, the volume decreases. The volume decreases. Okay, there's a decrease in volume from 1 to 2, simply meaning the volume, when volume is moving in this direction, volume is doing what? It is decreasing. When volume is moving in the left direction, it is decreasing. From 1 to 2, it's decreasing. From 2 to 1, it's increasing. Okay, and the temperature increases from T1 to T2, simply meaning there's now what we refer to a temperature increase from T1 to T2, simply meaning there's a reduction in volume, and then that reduction in volume, it actually gives us an increase in temperature. Okay, and then again from 2 to 3, air is delivered under pressure at V2. Okay, so at this point, that's where air is delivered under pressure at V2, and then this point also constitute as P2 as well as T2 for obvious reasons. Okay, then from 3 to 4, delivery closes and the suction valve opens, simply meaning when you move from 3 to 4, what's happening during the process of moving from 3 to 4, the delivery, it closes and the suction valve opens. So if the delivery is closing and the suction valve is opening, that means it is now sucking in. Okay, so it is sucking in, okay, for admitting fresh air inside the cylinder. Okay, so okay, right, so long story short, work is done. The work done, it is basically what you will normally find as the area under the graph. So simply meaning we refer to the graph, area under the graph, that constitutes as work done. And now here is the energy equation. H1 plus Q equals H2 plus W. Now Q is heat, W is work, and then H is what is referred to as enthalpy. Enthalpy, okay, right. H is referred to as enthalpy, right. So therefore, work is equal to the change in enthalpy plus heat. Okay, change in enthalpy, simply meaning H1 minus H2. Okay, right. Then also we will notice that work is equal to the mass of the gas, okay, plus the specific heat capacity, assuming constant pressure, multiplied by a variation in time, simply meaning T1 minus T1. In this case, it can be T2 minus T1, okay, right, plus we have that relationship on top, the relationship at the bottom, and then that is a multiple of this relationship at the top relative to the relationship at the bottom. Okay, so now long story short, what are we getting at? what we are getting at here is that when we refer to heat, this is heat. Looking at heat in terms of the condition of constant pressure. Okay, right? And then this over here, it speaks to our enthalpy, right? Enthalpy, right? So then also, this is our specific heat capacity constant as a function of pressure, assuming constant pressure, and then this is the specific heat capacity constant as a function of constant volume. Okay, and then that equates that variation, that difference, it equates into R, and then obviously there's a relationship there, and then from that relationship, this is just mathematical manipulation, and then for now we'll stop there. Okay, right, so as we continue, we notice that there's an expression over there once you do substitution, as well as an expression over there once you do substitution, since PV equals MRT. Okay, and then the work, it is then described by this expression over here. So we'll stop there for now.